In this video, we are going to talk about the reactions of alkanes. Now, the first thing to notice is that alkanes are non-polar, and therefore the intermolecular forces that hold alkane atoms together is the weak van der Waals forces. So, for example, let's use a cyclobutane. A cyclobutane is a non-polar molecule. So you will see that in terms of reaction, you cannot this alkane cannot go an addition reaction, and the weak van der Waals forces, their strength increases with increasing molecular mass. So you expect that the van der Waals forces that are within a pentane will be greater than the van der Waals forces that are within a butane. Now, increasing strength of van der Waals forces is correspondent or directly proportional to the increasing boiling point. So therefore, you will see that a normal pentane will have a higher boiling point than a butane. However, in alkanes, the strength of the van der Waals forces decreases with branching. So for example, if you have this normal pentane, and then you also have this molecule, which is a 2,2-dimethylpropane. And 2,2-dimethylpropane is an isomer of a normal pentane. You see that the boiling point of the 2,2-dimethylpropane is greater than the boiling point of the normal pentane. So the boiling point of the pentane from theory is 36 degrees Celsius, and then the boiling point of 2,2-dimethylpropane has a boiling point of 9.5 degrees Celsius. And the reason is what we have stated earlier, that branching in alkanes decreases the strength of the weak intermolecular van der Waals forces that holds the various atoms together, and therefore makes it have a lower boiling point, because boiling point is directly proportional to the strength of the van der Waals forces. Now, let us explain this observation. So, you see that the density rho of a normal butane is 0.626 gram per centimeter cube, and then the density of a cyclopentane is 0.75 grams per centimeter cube. So explain this observation. Why is it that a straight chain pentane has a smaller density compared to a cyclopentane, even though they all have the same number of carbons and hydrogens? And then the reason is because taking this pentane, if you have a unit volume here, you can pack, because this pentane is symmetrical, you can pack a lot of the cyclopentane in a small volume compared to the straight chain pentane. And because you can pack large number of cyclopentane in a small volume, then it means that per unit volume there are more cyclopentane molecules compared to the straight chain pentane, and therefore it will have a higher density than the straight chain pentane. So now, what are some of the synthesis of alkanes? Alkanes normally undergo a hydrogenation reaction to give straight chain alkanes. So if you have an alkene and you add hydrogen gas in platinum catalyst, the hydrogen gas gets substituted across the double bond. So therefore it will convert it to an alkane. So you see that we have moved from this alkene to an alkane. It is the same when you have an alkyne. So for example, let's take this alkyne. So this is an alkyne. So the difference is that with the alkene, we added 1 mole of hydrogen gas. But with the alkyne, we are going to add 2 moles of hydrogen gas in the same catalyst, platinum catalyst. And this time too, we are going to convert it into the straight chain alkane. So now, alkanes also undergo a reduction reaction. So for example, if you have a haloalkane like this, which is 1-bromobutane, and you put in this reagent known as lithium aluminium hydride, the reaction becomes a normal straight chain alkane, so which is a butane. At the end of the day, you have removed the bromide from the alkane. So you can reduce a haloalkane to get a normal straight chain alkane. Another reaction too is using the Grignard reagent. If we have this reaction, this is 1-chloropropane, and then what you do is that you put in a magnesium metal. The magnesium metal gets sandwiched between the carbon and then the chlorine. So the intermediate compound that is formed is this compound. So at the end of the day, if you treat it with water, then you are going to get your ethane, your propane here, and then magnesium chloride. So now, how do you convert an alkane? So let's take a propane to a haloalkane. So let's assume we add in chlorine gas, and we want to get a haloalkane like 1-chlorobutane. So this is chlorine gas, Cl2. How do we go through this process? Now, this process only happens under either heat or light. What is the mechanism for this reaction? This reaction comes in 3 steps. And the first step is the initiation step. And then the second step is the propagation step. And then the last step is the termination step. So anytime you are doing a monochlorination or a monobromination of any alkane, these are the 3 steps that it goes through. So in the initiation step, what happens is that the chlorine gas gets converted into its radicals. So for example, let me show it. So this is chlorine gas. Under light, maybe let's supply some energy to the chlorine gas. What happens is that these chlorine atoms are sharing 2 electrons. So the electrons are cleaved homolytically, such that 1 electron is moved to 1 chlorine atom and the other electron is moved to the other chlorine atom. So at the end of the day, you are going to create 2 chlorine radical atoms. So now, this radical will then come and then pick a proton. So this is what happens in the initiation step. Now let's talk about the propagation step. In the propagation step, what happens is that, so there is a proton here. This chlorine radical comes to pick a proton, but it also picks the proton homolytically. In this reaction, we only create radical, so it is a radical reaction. So there are two electrons between this carbon and hydrogen. So this chlorine atom and then this hydrogen will share the electrons that are here. So this electron will move to the carbon atom. So at the end of the day, we are going to get this propyl radical, then plus hydrogen chloride. Now, this propyl radical is unstable, so it will look for stability. And because there are a lot of chlorine gas in the system, then the propyl radical will come and pick a chlorine gas. So if it picks the chlorine gas, you will create a chloropropene, then plus a radical atom. Now remember that there are a lot of hydrogens on the propyl group. So because this is a radical, this reaction will continue indefinitely. And because you don't want it to continue indefinitely, you need to terminate or end the reaction. And that means, so this will lead us to the termination step. How do you terminate these reactions? In termination this reaction, you take each of the radicals and react them together and then to form their diatoms. So for example, we have a chlorine radical in this system. We can add it to another chlorine radical and this will give us a chlorine gas. Or we can also add this propyl radical to a chlorine radical to give us a chloropropene. Or another thing we can also do, let me continue from here, is we can take two propyl radicals and add them together. If we add two propyl radicals, we are going to get this compound. This is the monohalogenation of an alkane. However, this reaction favors the more substituted alkane. So because bromine gas and then the chlorine gas are very toxic and their reactions are normally uncontrollable, chemists tend to avoid them when doing a halogenation reaction. So what they normally use are the halogenation agents. So for example, one halogenation agent is this compound, which is known as sulfonyl chloride. So this is a sulfonyl chloride. And another halogenation agent is N-bromosuccinamide. So this is an N-bromosuccinamide. So there's a nitrogen atom here, so which is linked to a bromine. So this is N-bromosuccinamide. So these are the halogenation agents. Now, with the halogenation agents, you will not get the chlorine or bromine radical until you use the radical initiator. So one example of a radical initiator is, this is called a dibenzoyl peroxide. So it is a halogenation agent because under heat, this compound can easily cleave at this point to give you a radical. So if you put in heat or UV light, this can easily cleave to give you this radical, an oxygen radical. And then this radical can then attack a sulfonyl chloride. And when it attacks the sulfonyl chloride, it will release a chlorine radical. So it will release this chlorine radical, and it is this chlorine radical that then goes into solution to perform the halogenation reaction. Another radical initiator is the azo by bis isobutyrylnitrile. And we have this question here. For each of the following compounds, predict the major product formed in free radical bromination. The first one is methyl cyclohexane. The second one is ethyl benzene. And the third one is 2,2,3 trimethylbutane. So let's try and draw the various compounds. So methyl cyclohexane. This is a methyl cyclohexane, CH3. And we have benzene. So this is a mistake. Ethyl benzene. So this is an ethyl benzene. So benzene group that is attached to a CH2 CH3 group. And then the last one is 2,2,3 trimethylbutane. So this is butane. And then we have a CH3 on carbon number 2, another CH3 on carbon number 2, and then we have a CH3 on carbon number 3. So this is 2,2,3 trimethylbutane. Now, in halogenation reaction, the reaction tends to favor the more substituted alkane. Primary protons, secondary protons, tertiary protons. So now, anytime you see a CH3, the protons that are on a CH3 are all primary protons. And the protons that are on a CH2 are secondary protons. And then the protons that are on a CH, this proton is a tertiary proton. In the halogenation reaction, you see that it is a proton that gets substituted. So the number of products that will be formed for each compound depends on the number of different types of protons that the compound has. So if you take the first part, the methyl cyclohexane, you see that we have a CH compound here, we have a CH here. So this CH is a tertiary proton. So this is a tertiary proton. We have a CH3 here, which is a primary proton. And then this is a CH2 because there are 2 protons here. And this is a secondary proton. So it implies that a methyl cyclohexane will form 3 different products. One of the products are this one, which is one of these protons will get substituted. So we get a CH2Br. And then the second product that will form is this product. So there's a CH3 here. So this proton that was here, the tertiary proton, will also get substituted. So there is a Br here. And then the last product that will form is when one of these protons gets substituted. So there's a CH3 here. And so here is a Br. So these are the 3 different products that will form from the monobromination of methyl cyclohexane. Nonetheless, which of these 3 is the most stable product or the major product? Now, the major product usually favors the most stable product. Now, primary hydrogens are less stable than secondary hydrogens, which is in turn less stable than tertiary hydrogens. So therefore, you see that this is a primary hydrogen. This will be the least stable product. And then this is a secondary hydrogen. This compound is coming from the secondary hydrogen. And therefore, this will also be less stable compared to this product, which is coming from a tertiary hydrogen. And therefore, the most stable or the major product. So this is the most stable, and then the most stable product will form the major product. So this is the major product. Now let's come to this. How many different protons are on this compound, ethyl benzene? So you see that there are protons here which are replicated throughout this cyclic ring, but there is no proton here. And then you see that this proton is a secondary proton, and this is a primary proton, and then this is a tertiary proton. So you see that in this case too, we will have 3 different products. You can pause the video and try writing the product. So we are going to have one of the products will be this product, which is CHBr, then CH3. This is one of the products that we are going to form. And then that one is coming from the secondary protons. And then the other product will be the product coming from the primary protons. So this will be CH2CH2Br. So this is the other product that we will form. And then the last one will be the one coming from the tertiary proton. And that is, there's an ethyl group here, which is CH2CH3. This is a benzene ring, and this is Br. So as we have established, the most stable products are the products that are coming from the tertiary proton. So, and then the most stable product is the major product. So you see that this one is the tertiary proton, and therefore this becomes the major product. Now let's come to this case too. So you see that this is a primary proton. This carbon, all of the protons on it are primary protons. Likewise this. Likewise this one too. And likewise this. And then this one too also has 3 protons. But you see that there is a proton here. This proton. And this proton is a tertiary proton, CH. So we have 2 kinds of protons that are on this molecule. We only have primary protons and tertiary protons. And because we have only primary and tertiary protons, we will only form 2 products in the bromination of this compound. So not like the first ones that we formed 3. So the only product that we are going to form is this product. So let me write it up here. So we can form one of these products. So there is a CH3 here, CH3 here. Either one of these protons can get substituted by the bromine. So there is also a CH3 here. So this is a CH3. And then there is a CH3 here. Then let me write CH2Br. So this is one of the products that can form. And then the one by the tertiary proton. So let me write that product here, which is this product. So there is CH3, CH3, and CH3 is also here. Then here is Br, and we have a CH3 here, and then a CH3 here. So these are the 2 different kinds of different products that can form. So between these 2, this one is coming from a primary proton. It implies that this compound is less stable than this one, which is coming from a tertiary proton. And therefore the most stable product or the major product is this compound. So this is the major product, and then this is the minor product.